Nima, for the thank you very much, Nima, for the kind introduction. Thank you also for inviting me to speak here. This has been a wonderful series of webinars, the ones that I've been able to follow. So thanks for organizing that. And I very much concur with all of the motivations that you've listed for this. I think it's very important that these traditionally separate, coming from different backgrounds, communities that are working on relevant problems talk to each other and discover synergies and ideas. And in that, on that note, my group, as was mentioned at Northwestern, we work on various levels of topics that are relevant to emerging computing systems. So we have a lot of work going on materials, new types of materials, new types of devices, but we're also very interested in exploring circuits and architectures based on those devices. And I think what you will see is that this talk is perhaps more device focused than some of the other others in this series. So I would like to ask you all to bear with me as I go through some device physics. But my hope is that that will help convey some ideas and perhaps spark discussions. And I very much look forward to feedback from the designers and architects in the audience. So what I thought I could discuss today is our work on voltage controlled magnetic devices and how they might be useful for computing. Particularly, we are working on a new type of MRAM that we refer to as voltage controlled MRAM. Here, when I say voltage controlled, I mean as opposed to current controlled. So voltage meaning electric fields. And so in addition to essentially building quote unquote conventional memory devices that are controlled by electric fields, magnetic devices that are controlled by electric fields, we are also quite interested in using the inherent stochasticity of these magnetic elements, which is a feature or a bug, depending how you look at it. If you want to build a reliable memory, of course, the stochasticity of nanomagnets is a bug that needs to be addressed because it causes errors, but it can also be a feature, and I will try to point out some of the work that we are doing in that area. So I don't think for this audience I need to say too much about the motivation, but the way we look at this is that if you look at any kind of data-intensive computing task, and machine learning is a great example of that, these current implementations are basically very, very inefficient in terms of energy. So if you look at a typical state-of-the-art machine learning system, this one I'm showing is from a few years ago, but numbers are not that different today. It's about 2 to 5 orders of magnitude more energy hungry than a human brain. And of course, a human brain does a lot more than, say, play a game or drive a car. And so this lack of energy efficiency is particularly a problem with the transition from the cloud infrastructure to edge kind of devices where there is less abundant energy sources available, and also the cooling infrastructure that is available, of course, in the cloud environment is not as readily accessible. So there is a need to bridge that gap. And as again has been pointed out, I think by essentially all of the speakers in this series, a lot of this energy inefficiency can be traced back to the way that computing is organized, and this is essentially one of the key reasons for this interest in memory computing and all of its various incarnations and definitions, which is to overcome the memory wall, right? The memory bottleneck. If you can put more data close to the processor, if you're doing computing in a kind of traditional processor logic core, if you have more data close to it, meaning if you have a bigger embedded cache on the same chip, for example, then you can have a more energy efficient and a higher performance kind of compute. And then also, once you have these new devices, you can think about how you can actually use these memory devices now for computing, and that also minimizes the back and forth between the traditional logic and memory, and again, that can boost performance. The bigger the data sets are, the more advantage roughly you can expect to get from these kinds of new emerging ways of doing computing. And this is really important if you look at the numbers, if you look at, for example, the size of a particular AI task over time, the size of these neural networks is growing exponentially at a rate that is faster even than Moore's law in its best days, let alone now. And so it's clear that at least we think that the traditional scaling approach and the traditional way of using only conventional existing devices may not cut it. And so there's definitely a need for exploring emerging types of devices that can be combined with existing semiconductor substrates, front ends. So that's essentially one of the key reasons that there's so much interest in MRAM by the semiconductor industry. The magnetic random access memory has been heavily invested in over the past decades. Essentially, all of the major foundries either have it in production or have it close to production today. And one of the big driving forces behind that has been essentially this problem statement that I just described. Even though in its current form, the early adoption of MRAM in the industry is primarily driven by its non-volatility, not so much by its high density versus SRAM, which I will get to the reason for that in a moment. But essentially, this is an exciting time to be exploring these magnetic devices because they are no longer kind of theoretical lab devices. They are in fact, being put into high volume manufacturing. And so we can really think about how we can perhaps use them in unconventional ways now. So to point out both the promise and the limitations of today's MRAM, which will allow me to segue into why we are working on a voltage-controlled version of these devices. I think it's useful to kind of look at this qualitative picture I have here, which illustrates the fundamental trade-off that exists among essentially all existing memory and storage devices between density, or you could say cost per bit, on the one axis and speed on the other. So on the one end, you have very fast devices or very fast technologies, I should say, like SRAM, which basically are the fastest memories we have. On the other hand, these are very expensive. You need 6 to 8 transistors typically for 1 bit of information, so that makes it very low density. The other extreme is, of course, storage, right? You have very cheap storage cost per bit, but it's very slow, and that's true for NAND flash, solid state drives. It's even farther to the top left for hard disk drives, for example, or tape. And where we would like to be, obviously, is the top right? So we're looking for something that hopefully is dense but also fast, and that would allow us to really put more embedded memories directly on any processor. Today's MRAM, which is based on a principle called spin transfer torque, so it's called STT-MRAM, essentially falls somewhere between DRAM and SRAM in terms of both of these attributes, in terms of speed and density. And it suffers from a fundamental trade-off between density and speed. So essentially, trying to make today's MRAMs faster would also make them more expensive and lower density. The reason for that is essentially apparent from the structure of a 1-bit cell of an STT-MRAM that I'm showing here. So essentially, you have a magnetic device called a magnetic tunnel junction, where you have 2 magnetic layers, one of which can be switched. And so depending on the relative orientation of the two, you have a high or low state resistance. This effect is called TMR, tunneling magnetoresistance, and it's what allows you to read out the information. So it allows you to turn the magnetic state of the free layer, which is the one that you can switch, into an electrical signal. To write information into this structure in order to basically to switch the free layer, you pass currents through this structure. And if you pass currents one way or the other, it will basically, through transfer of angular momentum to the free layer, it will switch it in one direction or the other. And that is basically the essence of the spin transfer torque effect. Now, that current has to be provided by a transistor, which is basically put in series with as a select device with this magnetic tunnel junction. Now, the challenge is that the faster you want to switch, the more current you need, and therefore the bigger the transistor has to be. So essentially, in order to achieve higher write speeds with today's STT-MRAM, you have to use bigger transistors, and therefore you sacrifice density. So there is this fundamental trade-off between the two. What is also very important is that you have this ultra-thin oxide within the structure separating the two magnetic layers, and if you pass large currents through it, there is a chance that this oxide will wear out over time. So for these reasons, while STT-MRAM is in production today, we're looking at, basically my group and many others in the community are looking at physical concepts and materials beyond the conventional version of MRAM today that could still have a minimal deviation in terms of manufacturing from what is being employed today, so that essentially all of that investment that has been already made can be used. So there's minimum additional or no additional capex required, but would allow us to really push towards this top right. And among the things that I would like to highlight, the first one is voltage controlled devices. So if we had devices where we essentially can control the magnetic state using the electric field, using the voltage rather than by passing the currents through the device, in principle, you could always use a minimum size transistor. All you need is to apply a particular voltage. So in other words, the write current in that case could approach zero, and that would be very attractive. So that is kind of the bulk of what I will be talking about, variations of these kinds of devices. Secondly, there is, especially if you think about very high density types of MRAMs, another challenge is the magnetic interaction between these bits. This is something that has been seen for essentially DRAM-like density MRAM test chips that have been built a few years ago, where these magnetic bits basically start interacting because they are magnets, they have magnetic fields emanating from them, and this causes errors. And for this reason, we are interested in working on antiferromagnets, which are basically materials that are magnetically ordered. They can store information in a non-volatile way, just like your conventional magnets, but have no magnetic fields emanating from them, and therefore could be very useful for these high density applications. This is all kind of at the device and technology level, but basically once you have these devices, then there is a lot of new physics, new features, the stochasticity being a key example, that allow you to think about how you could architect computing now in new ways, and really not just try to replace the existing kinds of technologies that are out there, but try to develop ideas based on the unique physics of these new devices. Again, once they can be manufactured in volume, there is, I think there will be a lot of possibilities of exploring ideas of this kind. So basically, what I would like to do is first to explain how our version of this voltage-controlled MRAM works, and I will show you some devices that we've developed on this. Then I will segue into how those devices could be used in the context of stochastic computing and building artificial neural networks based on those. And then if time allows, I will go back to talking a little bit about our work on antiferromagnets, and particularly using the high-speed dynamics of those materials to, in the context again of improving the performance of stochastic circuits that you could build based on these devices. So here I'm showing two variations of these magnetic tunnel junctions that I just talked about on the previous slide. Don't worry about the equations, but basically what I'm trying to illustrate here is that you can have two variations where the magnetization is either in plane or out of plane. So the early generations of MRAM, the magnetization of the magnetic material was basically in the plane of the sample, parallel to its interfaces. In the newer versions, which are the ones that have been adopted in industry, are perpendicular, and that has to do with improved scaling. The basic way that these magnetizations become perpendicular is by relying on interface effects. So the spins, the electron spins in a magnetic material in proximity to its neighbors, in particular if that neighbor is an oxide, tend to like to align themselves out of plane rather than in the plane of the sample. And this is the same effect, the same physical effect that we use in order to achieve voltage control of magnetism. Basically, one way of looking at this structure, two magnetic layers, which are metals, cobalt, iron, boron, separated by an insulator, is as a capacitor. So if that middle layer is thin enough, which is always the case in present devices, you have tunneling currents through the structure, so you can look at it as a resistor. But if you make that insulator a little bit thicker, the resistance goes up and the device becomes more of a capacitor. So essentially you apply a voltage, you don't have that much tunneling, but you have charge accumulation on the two interfaces of the MgO, of the magnesium oxide insulator, and its neighbors. And by manipulating those interfaces in that way, by adding or depleting charges from it, you can change the magnetic properties of your magnetic layer. In particular, you can change the tendency of the spins to be in plane versus out of plane. And this is an effect called voltage-controlled magnetic anisotropy. So the magnetic anisotropy of that material is a function of a voltage applied across this capacitive element now. So this so-called VCMA effect can be used not just to reorient the magnetization from out of plane to in plane and back, but it can also be used to actually switch it by 180 degrees. And this can be achieved by timing the pulse that you apply. So if you apply a voltage pulse that is precisely timed, you can excite the magnetization into a resonant motion, where basically if the voltage pulse width coincides with half a precession period, half a resonance period of that magnetic motion, you can flip it by 180 degrees. So this is what's shown here. And this was something that was demonstrated by us and by other groups around the same time, and around 10 years ago or so. It's a very qualitatively very different way of switching a memory compared even to other MRAMs, compared even to the spin transfer torque MRAM that I just talked about. As far as building a reliable memory, which is not the focus today, I just point out to some of the papers that are relevant here. This kind of switching requires a pre-read step because it flips the bit by 180 degrees no matter what. So it's essentially a toggle kind of switching. So the read circuitry and having a fast read circuitry is very important. And also controlling the distributions between devices. So making sure that all devices indeed have the same precession period, so that the timing of the pulse can be done correctly, is also a challenge. And so the circuitry around it in order to make a reliable memory has to be quite different. And again, I will not go into the details of that other than to list of papers here. But basically, I have a couple of slides on how the switching in these devices indeed works. This is a result from 5 or 6 years ago, some of the initial devices that where we demonstrated this effect. So basically, what we're measuring here is the probability of switching. Again, because these are stochastic elements, the probability is never 100%. We measure the probability of switching as a function of the amplitude and width of the voltage pulse that we apply. Essentially, this is just done by doing a very large number of repeats of the right attempts and measuring the resistance of the device after each right attempt. What you can see, the general feature of these curves that I'm showing here, which is switching in one direction on the left, in the opposite direction in the middle, and then the product of the two basically on the right, is that it's oscillating as a function of the pulse width. And this is exactly what you would expect if you have a switching that is based on resonance, right? So you have a window in terms of the pulse width where you get reliable switching. And if you hit times that are outside of that window, in fact, you may actually get no switching at all or very low probability of switching. What you will also notice is that the switching probability does not really get very close to 1. These are, of course, not the best devices. You have maybe errors of several percent. You can make this considerably better, and that's kind of a push for conventional, reliable memory device development. But I think this very nicely illustrates the stochastic nature of these devices, is that you have basically a probability that is not 100% and that is really tunable between nearly 100% of switching and 100% almost of not switching as a function of pulse width. Incidentally, these devices, because they have very high resistances, again, because we're not relying on the spin transfer torque effect, are also very energy efficient. And so the switching energy at the individual device level is a few femtojoules per bit, which is extremely small compared to other non-volatile memories at this size. Now, one of the things that we're quite interested in is to increase this efficiency of this BCMA effect, which basically affects what kind of voltage you need to apply to this device. So you notice that in this device, we have a switching voltage of about 2 volts, which is high, especially if you want to put this in a logic process. Of course, this is quite high, and this depends essentially on the so-called VCMA coefficient, which I alluded to here, which is basically to say how sensitive are your magnetic properties, how sensitive is the magnetic anisotropy to voltage. So we've been working on this problem over the past few years, and this is the most recent results that we have, where we've achieved a VCMA efficiency that's about 3 times larger than previously published results in fully developed MRAM cells, in the sense that these are not just optimized for VCMA, but they also have a high TMR ratio. They have the right thermal stability to be able to be integrated into advanced CMOS processes in the back end of line. We've also reduced the bit diameter to 30 nanometers. So these are, in fact, slightly smaller than the STT-MRAM bits that are in production today. And with these, we've, for the first time, in fact, achieved VCMA-based switching below 1 volt. And we think that testing is ongoing on these chips. So we think that we should be able to, in fact, get these to be below 0.6 or 0.7 volts or so with the same materials. So that's kind of a very quick overview of our state of development of voltage-controlled MRAM. But as I mentioned, before I get to the next thing, I should also mention that while we have not yet built a voltage-controlled MRAM chip integrated with all the CMOS circuitry, we've done quite a bit of circuit level design and simulation work to kind of understand how the bit level performance translates into array level. And what I would like to highlight here, these are basically numbers based on a simulated 256 kilobit macro, comparing spin transfer torque, which is the current controlled version, VCMA, which is our voltage controlled version, and conventional SRAM. Essentially, the density advantage is apparent, and this is the one I'm showing here on the bottom left, where the voltage controlled version not only has an advantage compared to SRAM, but also compared to the current controlled version of MRAM. And this in fact improves in principle as you go to more advanced nodes. But what I would like to spend the next few minutes talking about is kind of elaborating on the stochastic nature of these devices. Again, as you saw here, the switching probabilities are not 100%. And the reason for that can be traced back to kind of this energy diagram that I have here. So you can think of these nanomagnets that we're switching essentially as being bistable devices where you have two energy minima. So the spins like to point one way or the other, which are indicated as 0 or 180 degrees, right? And normally these devices are non-volatile because you have some energy barrier between these two, which is large enough. So essentially thermal noise cannot overcome this energy barrier and flip the magnetization from one state to the other. So a large enough energy barrier allows you to have a non-volatile operation. At the same time, this energy barrier is not infinite. So if you wait long enough, any MRAM bit will flip because of thermal noise, right? So at some point, the thermal environment will provide enough energy to the spin to flip across this, and so that is, again, if you want to build a long-term storage with these elements, is something that needs to be accounted for, so that you need to have a large enough a minimum energy barrier in all of your bits. But if you're interested in building a stochastic device, for example, say a random number generator, the simplest thing you could do in terms of stochasticity, then you can intentionally reduce this energy barrier to the level that, say, every few seconds or every few milliseconds or every few microseconds, the spins will just thermally flip from one state to the other. And this will not be, there will not be a well-defined period to that oscillation. So, but there would be a mean time to switching that depends on the size of this energy barrier. So statistically, you know what the mean time for flipping from one state to the other is, but that flipping will be completely random and driven by thermal noise. So that is one way, which we refer to as thermally activated stochastic behavior. The other way that you could do this is essentially a variation of this voltage-induced switching behavior that I just described. So when we time our pulses, basically we can maximize the chance of the device flipping to its opposite state, flipping by 180 degrees. But something else that you could do is you can apply a voltage, and instead of terminating it, say, after half a nanosecond or 1 nanosecond, whatever that optimum time for switching happens to be, if you wait for a few nanoseconds, what will happen is essentially you are eliminating this energy barrier while you have the voltage in place. And what that results in is that you will get an exactly 50% probability of then the device equilibrating to one state or the other once you remove the voltage. So basically, this allows you then to achieve pretty fast random number generation. So you apply a pulse, you wait a few nanoseconds for the oscillations to die out. And then when you remove the pulse, the device has an equal probability of going to one state or the other. So we in fact designed random number generators based on this approach a few years ago, which is where essentially the benefit is, unlike the thermally activated version, which I talked about first, where you have to wait for thermal noise to flip the device. The second method is in principle faster. So here you're essentially controlling the bit rate with the clock in the system, right? So whenever you apply a voltage pulse, you get a random number out of your devices. Of course, you can design circuits that then translate that random resistance state into a random bit sequence. And in addition to the throughput, which can be pretty high, especially if you have an array of these devices rather than just one device, the area also can be very small, because your random number generator essentially is not a circuit. It's a nanoscale memory element that is generating those random numbers, and therefore you can have a pretty high throughput, pretty small area, true random number generators. So these basically translate thermal noise to random voltage. So they are true random number generators. So, well, what can we do other than generating random numbers? Well, one of the things that we thought might be interesting is to explore using these devices then for stochastic computing. Stochastic computing is not a new idea. It's been around for a long time, and it is, the basic idea is that you can, if you encoded if you encoded numbers rather than in the usual binary way that we do today, if you encoded them as probabilities of numbers between 0 and 1 or -1 to 1, then your basic multiplication and addition operations become very efficient. They become very simple bitwise logic operations. The simplest example of that is, say, if I encoded numbers between the range of 0 to 1 as a simple probability. So say, for example, 0.7 uh, um, would correspond to having, say, 700 out of 1,000 bits in a bit stream being 1. Of course, I don't know which 700 are ones and which 300 are zeros. But if I knew that the probability of finding ones in that random bit stream was 0.7, and then I had another bit stream where it was 0.6, for example, so 600 of them were ones, then just by doing a bitwise AND operation on the two, I would get a multiplication. So I would get a bit sequence that is very nearly, approximately, of course, but very nearly the product of the two. You can do similar operations where you encode this in the range of -1 to 1, which is beneficial if you want to use operations where you have subtraction and addition, of course. And then you basically can show that, again, additional multiplication on these on numbers encoded in this way can be very efficient. So we think that this could be a way to build very efficient neural networks, where, of course, addition and multiplication is all you do, right? So you have if you have a circuit where these two operations occur very frequently, then being able to reduce that circuitry to a simple logic could have benefits in terms of area, but also in terms of energy. And this could be, for example, again, useful in the context of edge machine learning, where you don't have as much energy or oftentimes also area available as you do in the cloud. The challenge, again, this is not a new idea. The challenge with this is that you need bit streams that are truly stochastic, truly random, and statistically independent of each other. So if there is any kind of correlation between the stochastic bit streams that you're using in different parts of your circuit, that will end up hurting the accuracy of the results, because this is an approximate computing method that relies on that statistical independence of those bit streams. And so we thought that this could be a very nice fit for these magnetic random number generators that we have, where essentially the randomness is true randomness, and they're completely statistically independent. So if you take two magnetic tunnel junctions, two MRAM bits that are unstable, and you measure the bit sequence from the two, there is absolutely no correlation between them. Again, because it's driven by thermal noise. So what we did was we took some devices and we implemented this, in this case, not using the voltage-controlled dynamic way of controlling, of creating random numbers that I mentioned a moment ago, but using the simpler thermal version. So essentially, these are bits that were designed to have a low energy barrier so that they had essentially a very short retention time, and they had a mean switching time of flipping between the two bits on the order of a millisecond or so. Importantly, if you have a device like that, then the conventional spin transfer torque effect that would be used normally to switch in a memory device can essentially tailor the probabilities. And it can basically allow you, by applying a pretty small current on the order of less than 5 microamps or so, to tailor the probability of finding bits in this bit stream from essentially being all zeros to all being ones. And this is just controlled by the analog voltage that you apply to the device. So the result is you have these random bit streams where if you don't apply a voltage to the device, essentially it spends about half its time in a zero state and about half its time in the one state. And it's flipping back and forth randomly. But then if you apply a voltage with one polarity or the other, it will basically go to being mostly in its high resistance state or mostly in its low resistance state. And then this is translated into this probability curve that is measured on these bit streams. So using these bit streams, then you can basically implement these stochastic operations. So if you had, say, a neural network, you can encode all of your inputs and all of your weights in terms of these stochastic numbers. And this is exactly what we did. So we took 6 magnetic tunnel junctions, 6 MRAM bits, to generate these bit streams. And we used a pair of MRAM bits in each layer. The reason for that being that simply we could get a better number resolution by multiplying the bit streams from 2 bits. And we basically, in order to make sure that statistical independence was there, we used 2 of these to encode the input numbers, 2 for the weights in each layer. And the training of this network was done in the conventional way. So there was we did not change the weights, the stochastic weights in real time. This was done, in fact, in a conventional way. But then the trained weights were translated into these stochastic bit streams that were measured using these MTJs. And with this, we basically implemented a pretty simple neural network where we showed that, for example, on the MNIST data set, it achieved pretty good accuracy in terms of handwritten number recognition. Not surprisingly, the length of the bit streams matters a lot here. The longer the bit streams are that you measure from these MTJs, so the longer you wait to get a longer bit stream, the better the training accuracy. But I think one of the important, perhaps, advantages of this, we think, could be that you have a way to adjust essentially the accuracy in real time. So because you're generating these weights in real time from the thermal oscillations of these MRAM bits, you can essentially adjust the bit stream length. It basically means just the time that you're measuring each bit, and that provides a real-time trade-off between energy and accuracy. And again, so you can sacrifice accuracy if you are in an energy constrained environment without doing any changes about the training or otherwise. So this is indeed real time, and we think that this could be having that trade-off in real time could be useful. That's basically I think all I had on this part. And the last few minutes, I'd like to talk about what I mentioned at the early in the early part of the presentation on antiferromagnets. So I mentioned that there is an interest in developing MRAMs based on materials that essentially have no or very small macroscopic magnetic fields emanating from them, very small magnetization. And these are basically called antiferromagnets, these types of materials. These are magnetically ordered materials where essentially each two neighboring spins are anti-parallel to each other. So you can think of basically because each two neighboring spins are anti-parallel, overall, it doesn't look like a magnetic material if you look at it from the distance, if you look at it macroscopically, but it does store information just like in conventional ferromagnets that are used in MRAM. And what we've been, this is, of course, it's a very interesting topic in terms of the material science and physics of these devices, which I will not go into, but we've been working on essentially spin orbit torque kind of devices, which is essentially another current-controlled way of controlling magnetism. That use antiferromagnets rather than ferromagnets for storing information. And what we were able to show last year was that indeed, if you take antiferromagnets that can be integrated in a pretty straightforward way on CMOS. These are sputter deposited using essentially standard manufacturing equipment for MRAM. These can store information and they can be switched using currents. And this was by no means obvious at the time. The conventional wisdom until a few years ago was that if a material does not have macroscopic magnetization, you can't control it electrically. And this has been a lot of interesting work that's been done these past few years showed that no, indeed, you can control these electrically and you can also read them out electrically. And so you could actually build memory devices with these. The interesting thing about them is that no matter how closely you place two of these bits together, they will not interact. So neighboring bits do not cause errors into their neighboring bits. And another interesting feature is that they're completely immune to external magnetic fields. So we took these devices and we put them in a field of 15 Tesla, which is much larger than you would see in any real application. And basically the data is unperturbed. Nothing changes in the device because the device does not have any interaction with magnetic fields. It does interact with electrical signals, so electric currents and voltages, but not with magnetic fields. We did this in a number of devices. Here I'm showing two kind of a slightly different version of this in a different metallic antiferromagnet that we did recently. And this is a differential measurement that we did on two neighboring devices, again, showing that this can be reliably done. Also with a differential readout where you get pretty good output characteristics. Again, I will not go into the details of this right now. But I think how this connects again to the stochastic devices that I talked about is that antiferromagnets have two interesting characteristics which we think will make them very, very interesting for these kinds of stochastic computing applications. Firstly, they exhibit the same kinds of voltage and current control torques as ferromagnets do. So BCMA exists also with antiferromagnets. Current-controlled switching of antiferromagnets is possible. So in principle, current-controlled stochasticity should also be possible in the same way. And what really distinguishes antiferromagnets is that they have dynamics that occur in hundreds of gigahertz or terahertz range frequency. And this is just because of the inherent basically dynamics of the spins in these materials, they have dynamics that are 2 to 3 orders of magnitude faster than ferromagnets, which are the ones used in today's MRAM. So if you think about it, if you have an MRAM today that typically would switch in half a nanosecond or 1 nanosecond or a few nanoseconds, these devices would switch or would provide you, conversely, provide you bit streams rather than at a rate of being a gigabit per second or so. These could be at the rates of hundreds of gigabit per second per device. And then if you imagine building arrays of these, you could in fact have very, very high throughputs for the stochastic bitstream generation, which directly translates into being able to address bigger problems with these stochastic neural networks that I just described. This is an idea where, again, some basic experiments have been done by us and by others in recent years. Exploring the stochasticity of these devices is not something that we've done yet, but we've done quite a bit of modeling. And we've shown that indeed, if you, with this kind of voltage-controlled a principle similar to ferromagnets, here we indeed should have switching at the time scales of 20 picoseconds or so, if we were interested to build a memory with this. But at the same time, if you basically use these vanishing oscillations, just like we did in the case of the ferromagnets, we should be able to also build random number generators with these devices that have extremely high bit rates. So this is basically the summary, and what I've just listed the main papers here. If you're interested, basically what hopefully I was able to convey to some extent was, firstly, how the stochastic features of MRAM could be a feature rather than a bug if we're trying to do efficient computing. How we may be able to increase the throughput by developing new materials that are still compatible with the same manufacturing methods as today's MRAM. And lastly, also that we've made basically the lowest voltage switching in a voltage-controlled MRAM that we're aware of in a very recent work. I'd like to end by just thanking some of the key people. My PhD student, Yixin Zhao, did a lot of the work on these MRAM bits and on the stochastic computing demonstration, with significant help from my postdoc, Victor Lopez Dominguez, and several of other students in my group that are listed here. I'd also like to, of course, thank the sponsors and partners. So the work was primarily supported by the National Science Foundation. Our work on anti-ferromagnets is also in part supported by the Materials Research Center at Northwestern. And both of these are also supported by industry sponsors and partners that we have. And I'd like to highlight our MRAM collaboration with Western Digital that has been going on for several years and was key to a lot of the results that I showed here. So I will go back to this summary slide, just leave it up here. Thank you for listening to me, and I look forward to any questions.
Excellent. Thank you very much, Pedram, for the very interesting talk. I guess we will now move to the questions and the panel discussions. Thank you once again. Let me stop also the recording.